So this is the Waves Homework Booklet question 21. We've got a diagram showing the cross-section through a step index optical fibre, and you're asked to name both parts A, which you'll notice is there, top and bottom, and B. For 1 mark, it's A is the cladding and B is the core. Very straightforward start there. On the diagram above, draw the path of a ray of light through the fibre. Assume the light ray undergoes total internal reflection at the boundary between A and B. As it's coming in at this point here, the light rays coming in, if you imagine doing the thumb and finger exercise, whichever's lower down is going to be carry on travelling faster for longer, so it's going to bend that way. So we need it to bend as it comes in, so that it ends up with the angle of refraction being smaller than the angle. There's the angle of refraction being smaller than the angle of incidence. That will then come through. Small angle there. Obviously, I really should have marked that relative to the normal, drawn normal on there, mark those on, but it should reflect off at that same angle, and I've put arrows on that to show that they're directions of travel. Calculate the critical angle for the boundary between A and B. Give your answers to an appropriate number of significant figures. Significant refractive index of part A is 146 and B 1.48. So it's simply using sine of theta c is n2 over n1. n2, the thing it's heading towards, which is A, 1.46. n1, the stuff it's currently travelling in, which is B, 1.48. That works out to that value, 0.9865. And then if that sine of that value is there, I've used the inverse sine function on the calculator to find that that is 80.6. My data is all to 3 significant figures here, so I've given my answer to 3 significant figures. State and explain one reason why part B, that was the core of the optical fibre, is made as narrow as possible. It's going to do 2 things for us. It's going to reduce modal dispersion, which would then cause pulse broadening, which reduces our maximum transmission rate. Another way of viewing it is it reduces the loss of light on curves, as it is more likely to keep angles above theta c. So modal dispersion, remember, is about taking different routes along the fibre, and essentially the narrower the core is, the fewer potential different routes there are, and so the less modal dispersion there'll be. I've got a little diagram to try and illustrate the issue with a narrow core and less loss. So here's a relatively wide core that the light's travelling along, and the beam could be coming along here, and with that radius of curvature, as it comes along there, that's going to hit at a relatively small angle to the normal. That might well do some refraction, some light's lost. If I make that core much narrower, which I've tried to illustrate there, similar curvature, radius of curvature, certainly on the outside edge, and as that comes in, because it's a narrower beam, it's going to hit that edge sooner. It's going to mean that I've still got a larger angle. I'm more likely to carry on having total internal reflection. Finally, on question 21, one application of optical fibres and explain how it's benefited societies. So an application might be the use of endoscope, giving us improved medical diagnosis. Another application is in communications, where it's given us benefits of high-speed data connections. So that was the Waves Homework Booklet, question 21.